In section 3.3, we're looking more in depth at measures of variation. Anytime we describe a distribution, it's really important to give a measure of variation along with a measure of center. In these three data sets here, we can see that they all have the same mean. The mean of all of these is 15.5, but they're very different distributions. So knowing the variation tells us a lot about how spread out the data is. Now there's something called standard deviation, which is a measure of how spread out this data is. And we can see in this distribution, we have a standard deviation of 3.338. In the middle one, which is the least spread out, we have 0.9258. And this bottom one, which is the most spread out from the actual mean, we have the largest standard deviation. So before talking about what standard deviation is, let's start with the easiest measure of spread, which is the range. We find the range by taking the maximum, subtracting the minimum. That gives us a number, and that number is the range. Range is a single number. Range is really easy to find. However, it's very sensitive to outliers. Okay? It can give a distorted view of the data if outliers are present. So in other words, range is a bad measure of spread. We would only really want to report this in addition to something like the standard deviation. Now to define what standard deviation is, it's the average distance from the mean for an entire data set. Here's our equation of how we find it. It's a bit complicated, but the good news is that once we're through this chapter and we understand how it's found and what it is, we let the calculator do this work for us. The reason the standard deviation is the best measure of center is that it's calculated using every data value, the same way the mean was. The reason that we have issues with it is that it's sensitive to outliers, just like the mean, and it can be a bit of a pain to find. So we want to use standard deviation anytime we have an approximately symmetric or uniform distribution, something that's not skewed. We always pair it with the mean. So if we give the mean as the measure of center, we give the standard deviation as the measure of spread. A few more facts about standard deviation. The value of the standard deviation, which is denoted by the variable s, is never negative. The smallest it can be is 0, and it's only 0 when all the data values are the same. Okay? In every other situation, we're going to have a positive standard deviation telling us how spread out the data is. The larger the value of s is, that's telling us that there's greater amounts of variation. If it's smaller, there's less variation, meaning that all our data is clustered, more clustered around the mean. Okay, or standard deviation can increase dramatically once we have outliers present, and the units of the standard deviation are the same as the units of our original data values. So to get a better understanding of what exactly we're finding with standard deviation, let's do an example by hand. So in this example, we have a sample of 8 AP Statistics students who are asked the question, how many hours do you work over the summer? The values they reported are listed here, and the first step is to find the mean. This is a sample, so we're using x bar to denote the mean. If we add all of these values up, we have 130, and we divide that by how many there are, in this case, there's 8. Okay, that gives us a standard deviation, a mean of 16.25. So the first column in this table is showing x minus x bar. In other words, we're taking each data value and we're subtracting the mean that we just found, which was 16.25. 35 minus 16.25 gives us this value, 0 minus 16.25 gives us that value, etc. Now what we would want to do at this point is combine all these distances from the mean. But the problem is we can see some are positive, some are negative. So if we added all these up, they equal 0. They always equal 0. They cancel each other out. So we want to make them all positive, and to do that, we're just going to square whatever we got in this column. That'll change it to a positive number, and we can add all those together. So here we have those numbers plugged in, which again is just each of these numbers squared. Okay, and what we want to do now is take this whole column and add it all up. When we do that, we'll get 1185.5. The equation for standard deviation was on a previous slide. I have it rewritten here. We can see on the top of this fractions, it's the sum of x minus x bar squared. In other words, it's the sum of this whole column, which is the number we just found. Now we're going to almost average these. Okay, instead of dividing it by however many there are, we're dividing it by however many there are minus 1. So plugged in, we have 1185.5 over 8 minus 1. And when we do that, we get 169.357. Now this value, the 169.357, has its own name, and this is called the variance. Okay, it's what we get once we square everything and almost average them. Okay, this is really the square of the standard deviation because the last step is to square root it, and when we square root that number, we get our standard deviation of 13.014. So again, just to reiterate, 13.014 squared would give us 169.357, and that number is called the variance. Variance is a bit of an abstract concept. The larger it is, the more variation we have in our data set, but really we're dealing primarily with standard deviation instead of variance. Variance is just the standard deviation squared. If it's a sample, we use the variable s for standard deviation, so s squared for variance. If it's a population, or in other words, if we have the whole data set of everyone that we're interested in, we would use this symbol, which is sigma. It looks like that, kind of O with a little squiggly on top. Okay, so the variance of the population would be sigma squared. Right? The disadvantage of using variance is that the units are different than the units of the original data because we squared everything. We're actually working in units squared.